All right, so we're going to go ahead and start with a little bit of review from what we learned in class on Wednesday last week. And these problems here are going to involve mutually exclusive events and independent events. So where's my toolbar here? It's not what I'm looking for. There we go. All right, I'm going to write in black here. So it says E and F are mutually exclusive events. So we have to look for the keywords when we're doing these here. So we have mutually exclusive. And it says probability of E is equal to 0.4. The probability of F is equal to 0.5. Find the probability of E given F. So what does mutually exclusive mean? That means that both events cannot both happen, right? That means that they both cannot happen at the same time. So what that tells us is that if they're mutually exclusive, the probability of E and the probability of F is equal to 0. That's what we know for mutually exclusive, that both events cannot happen. So if we read this one carefully, we actually don't even need to know this information. This information here is actually irrelevant. And if we think about it, this is saying that what is the probability of E given F? So this tells us that F has already happened. So event F has already happened, right? So E given F tells us event F has already happened. That means event E cannot happen because it's mutually exclusive. Both events can't happen. So in this case, just by knowing that, the probability of E given F is 0 because these events are mutually exclusive, which means they both can't happen. So if F has already happened, then the probability of E is 0, can't happen. Now, if we use the formula that you learned in class, the probability of E given F would equal the probability of E and F divided by the probability of F. Now, in this case, because it's mutually exclusive, we know that the probability of E and F is 0. So we have 0 on the top divided by the probability of F, which was 0.5, and 0 divided by anything is 0. So that one's just 0. All right, let's take a look at the second one. It says J and K are independent events. So we get the information that they're independent events. We know that the probability of J given K is equal to 0.3. What's the probability of J? So again, we have to know the definition of independent events. That means that one event does not have any influence on the other event. So knowing that event J has happened does not change the probability of K happening. So because of this, if the probability of J given K is 0.3, right, that means that the probability of J is also 0.3. Because since J and K are independent, having K happen does not increase the chances of J. So in this case, the probability of J is still 0.3. All right, and then let's take a look at the third one. It says Q and R are independent events, right? So when events are independent, remember there's 3 different ways that we can show that the events are independent. And one of those 3 ways was we're able to show that the probability of J and, well, no, we don't have J in this case, we got Q and R. So if 2 events Q and R are independent, then that tells us that the probability of Q times the probability of R is going to be equal to the probability of Q and R, right? So if we just put the numbers in here in their appropriate spot in this equation, we can solve this one. So probability of Q is 0.4, so we'll put 0.4 right there in for the probability of Q. So that's going to be 0.4. We're solving for the probability of R, so I'm just going to let that be X. So we're going to have 0.4 times X is equal to the probability of Q and R, which is 0.1. So we get 0.4 times X equals 0.1, divide both sides by 0.4, and we get that X is equal to 0.1 over 0.4, which is going to be 0.25 if you do the math. So the probability of R is equal to 0.25 for that one.